This webcast looks at Worksheet 3E, where we are interpreting graphs of accelerated motion. We're starting to move beyond just descriptions of how the thing is moving and do some quantitative analysis, for example, calculating average velocities and things like that. Okay, so let's look here at 3E. In the first problem, we are given this graph, and it's very important to pay attention and to take note. What kind of graph do you have? Because you're going to interpret a position versus time graph very differently from a velocity versus time graph. Okay, so this is a position versus time graph, and I can see that it starts at position 0. First, it looks like it is it's starting at a pretty high rate of speed, because see, if I drew a tangent line here at the beginning, it would have a steep positive slope. It slows down as it moves in the positive direction. At point B, it starts to turn and go in the other direction. First, it is speeding up in the negative direction, and then it is slowing down in the negative direction. Around point D, it turns around again and starts moving in the positive direction. For a little bit of time, it is picking up speed, it's speeding up, and then from E to F, it is linear, and so that looks like it's traveling at a constant speed at the end in the positive direction. Okay, let's answer these questions about this graph. Where is the object moving at the slowest speed? So on the position versus time graph, it's the slope that indicates the velocity, and speed is, the magnitude of that velocity. So in order to tell the instantaneous speed, I'm going to use tangential lines, and I'm looking for places where the tangential line would be horizontal. Looks like there at point B might be one, and if I took like my pencil and held it against the curve, that would be a good way to, kind of see the slope of a tangential line. I see another point would be at point D. So both of these points are places where the speed and the velocity, I guess, is 0, because the tangent line is horizontal. Okay, so those would be the places where this object has the slowest speed. Both of those are just for an instant. It's at the point where the object is changing direction. Okay, in what range is velocity positive? Well, if velocity is positive, that means that the slope of the position versus time graph must be positive, and it looks to me like from A to B and also from D to F. So in those ranges, the velocity is positive and slope is positive, or, it's moving in the positive direction. And what about where it's negative? Well, it's negative from B to D, and kind of the opposite. Here, the slope is negative, and that means it's moving in a negative direction. Okay. In what ranges is acceleration positive? And the next question, in what ranges is acceleration negative? Now this is a little bit of a tricky question, because acceleration is 2 steps removed from position versus time, right? we have to take the slope of position versus time to get the velocity, and then you have to take the slope of velocity versus time to get acceleration. And I know that velocity and acceleration don't always point in the same direction, but we have a rule that says that when an object is speeding up, then acceleration and velocity point in the same direction. So there are two scenarios where acceleration would be positive. If it's speeding up in the positive direction, that means that velocity is going to be positive and acceleration would be positive. What if it's speeding up in the negative direction? If it's going in the negative direction, velocity points in the negative direction and acceleration points in the same way, right? Because anytime speeding up, they point in the same direction. So that would be an example where it is speeding, where the acceleration is negative, if the object is speeding up in the negative direction. And then we know that if the object is slowing down, acceleration points in the opposite direction as velocity. So if it were slowing down in the negative direction, velocity would be negative, but acceleration would be positive. And if it were slowing down in the positive direction, velocity would be positive, but acceleration would be negative. So we have to look at our position versus time graph and look for these situations happening. So I'm going to go back up here. From A to B, it's moving in the positive direction and it's slowing down. So from A to B, we have a slowing down in the positive direction. So that must mean that acceleration is negative in that part of the graph. Then from B to C, it's moving in the negative direction and speeding up. So that would be also an area where acceleration is negative. Okay, because it's moving in the negative direction, so velocity is in that direction, and since it's speeding up, acceleration is in the same direction. From C to D, it's moving in the negative direction, but the slope is getting less steep. So it's slowing down in the negative direction. And so that would be, that fits this criteria, which tells us that acceleration is positive. And then from D to E, it's moving in the positive direction and the slope is getting steeper, so it's speeding up. So D to E fits this last criteria for acceleration being positive, which is that it's speeding up in the positive direction. Now E to F, that doesn't fit any one of these categories. Let's deal with that in a minute. In what range is acceleration 0? Well, now that might be E to F, and right, because in that section of the graph, it's linear. And that means that velocity is constant. And if the velocity is constant, there is no change in velocity, so there's no acceleration. Okay, now we're going to do a little calculation. What's the average velocity from time 0 to time 3? Well, the definition of average velocity is the displacement divided by the elapsed time. And the displacement, when I have a position versus time graph, I can find displacement as the final position minus the initial position. So let's go see if we can find the final and initial position. So at time 3, the final position up here is around 57 meters. The initial position was 0. So I have 57 minus 0 meters, and that was done in 3 seconds. And so we get an average velocity of 19 meters per second. Okay, let's look at the next question here, where we have, now they're giving us a velocity versus time graph. And so I have to interpret this in a different way, right? If I look at this, I see the first value of velocity is 0. That doesn't mean it's starting at a position of 0. I don't know anything about the position of this object, but I know that it's starting from rest, because at time 0, the velocity is 0. That means it's not moving at time 0. For the first couple of seconds, the velocity gets bigger, so it's speeding up in the positive direction, right? I know it's moving in the positive direction because the sign of the velocity is positive. Then from B to C, it moves at a constant velocity of 2 meters per second. Then it starts slowing down. And something really important happens right here. The velocity passes through 0. So it has slowed down, and then at time 4, it starts turning around, and now it's moving in the negative direction. I know that because the velocity is negative, and the sign of the velocity matches the direction of motion. So it's moving in the negative direction, and it's speeding up until it gets down here to time 6, and then it's still moving in the negative direction, but it's starting to slow down. Okay, so what attribute of the velocity versus time graph gives us the acceleration? It's the slope. Okay, so if we want to look at the slope to find the acceleration, what is the acceleration at time 1 second? Well, if I look up here at the graph, I can see that at time 1, if I went over 1 second, the velocity goes up 1 meter per second. So the slope there is 1 meter per second, or meter per second squared. Okay, at time 2.5, we're right here, between B and C. The velocity versus time is a horizontal line there, and the slope of a horizontal line is 0. So there, the acceleration is 0 meters per second squared. At time 4, now at time 4, I had marked that. I know that's a special point because the velocity is changing signs there. But I just want to know the acceleration, and so I need to know the slope of this curve at that point. And I can see, now this one's a little more complicated, right? Like an individual square, I can't just go over 1 and see how much the change is, but I can take the difference from D to C. So at D it's at -4 meters per second, at C it's at 2, and it makes that change in 3 seconds. So acceleration is the final velocity minus the initial velocity over the elapsed time. And so that would be, let me just check those numbers again, -4 minus 2 meters per second, and it did that in 3 seconds. So that is -2 meters per second squared. So it has that same velocity for all of the points between C and D because the graph of velocity versus time is linear from C to D. And then from D to E, it took in 1, 2, 3, 4, 5, 6 seconds, the velocity increased by 3 meters per second. So that's 3 over 6 or 0.5 meters per second squared. Okay, which attribute of this velocity versus time graph gives me the displacement? Well, that's the area between velocity versus time graph and the x-axis. So let's use that to find the displacement from time 0 to time 12. Okay, so I'm going to go up here to where the graph is so that we can see it. The first thing I'm going to do is identify the x-axis. That's where velocity is 0. And then I'm going to shade in the area between the red graph, right? That's my velocity versus time graph, and that x-axis. And so I have one area that's above the x-axis, and I have an area that's below the x-axis. Now, the shapes are complicated. I'm going to call this A. That's a trapezoid. This other shape I'm going to have to divide into at least a couple because it's not just one trapezoid. So I'm going to call this B, and this works. This is a trapezoid, so I can call that C. Okay, so the area is here. A is 1/2 the base of the trapezoid, which is 4 seconds, plus, that's the long base, the short base is 1 second, and then the height is 2 meters per second. So 1/2 of 4 plus 1, so 1/2 of 5 is 2.5, times 2 is 5. Okay, so we get 5 meters. Then shape B, that's a triangle, that's a little easier. Half of the base, which is 2 seconds, times the height, which is -4 meters per second. So that would be -4, I'm sorry, meters. I don't want to lose that negative sign. And C is another trapezoid. The long base is -4. The shorter base is -1. And then the height is 1, 2, 3, 4, 5, 6. So that would be -15 meters. If I add all of those up, the total displacement would be 5 plus -4 plus -15 is -14 meters. What attribute of the velocity versus time graph tells me the direction that the object is moving? The sign. I'm going to put that in a box. The sign of the velocity. And I mean, is it positive or is it negative? That sign matches the direction. So if velocity is positive, it's moving in the positive direction. If velocity is negative, it's moving in the negative direction. So in this graph that they gave us, in what time periods is the object moving in the negative direction? Well, that would be when it's negative. So it starts going negative at time 4 here. That's where I put that green dot. And it stays negative for the rest of that graph. So from time 4 to 12 seconds, it's moving in the negative direction. Where does it change directions? At time 4 seconds, that's where velocity changes signs. Okay.